Welcome to the next session. Uh, Today we will be dealing with design of experiments. So I am sharing my presentation, my PPT, and we will discuss the concepts that we are going to cover under design of experiments. So uh, as the word suggests, there are two words, that is design, and another word is the experiment. So this is a part of broad topic that is known as research design. Research design is actually blueprint or framework for research plan of action. Means what we are going to cover under the research or the topic that we have selected, that will be covered. All the planning, all the stages related to the planning and the implementation is related to the research design. So it actually guides the research by presenting the blueprint or the framework for the research plan of action that tells us what exactly is to be done. Now, this research design can be broadly classified under two categories. One is non-experimental research design, and the other one is the experimental research design. So, in the non-experimental design, we have we have actually two designs. One is the exploratory research design, and the other one is the descriptive research design, where we describe something. And in the experimental research, we will be covering the topic in a broad manner. So this non-experimental research design actually takes what is given. Right? So the objective is either to explore or to describe the things. Right? So now we will be going with the experimental research design and the design of experiments that is related to that. So what is the difference between these two? As we have discussed here, we take what that is given. So it does not provide the causal relation. And here the experimental research design provides the causal relation. So as it is there in the next slide, we can say that the basis, causality is the basis of classification between experimental research design and the non-experimental research design. So in order to establish cause and effect relationship, right? So causality is actually the establishing cause and effect relationship. Okay. So it provides, so the experimental research design provides the causality or cause and effect relationship can be established through experimental research design. So now we will be discussing what are the conditions for making any causal statement. Causal statement means establishing the relationship between cause and effect. So the first one is the concomitant variation. It means if a variable changes, right? Suppose this is variable 1, and there is a simultaneous change in the variable 2, right? Means with the change of variable 1, variable 2 also changes, right? So that is known as they have concomitant variation, their variations are being related. Now we will be discussing whether the concomitant variation is a full-fledged condition for making the causal statement. Obviously, it is a necessary condition, means it is required for that, means on changing one variable, the other variable should change. But let us discuss whether it is a sufficient condition or not. So As we know, there is a concept that is known as spurious correlation, spurious regression, or nonsense correlation, or nonsense regression. So, in that case, two variables may show concomitant variation, but they are not necessarily related. They may be related to some other factors also. So, all the examples that we cover under um, nonsense correlation or spurious correlation, that comes under concomitant variation also. So definitely it provides the necessary condition, but not the sufficient condition. Right? Like we take an example. Suppose as per the data, it has been observed that there is a strong correlation between sale of the ice cream and the death because of drowning. Right? Means in the period where the sales of ice cream is high, then death because of drowning is also high. Right? So they give the impression of concomitant variation. When the sales of the ice cream is low, the death would also be low. Right? So they show the concomitant variation. But actually here what happened? Both are related to heat or temperature, right? So as the temperature or the uh, heat in the environment rises, the increase in the sale, there is increase in the sale of the ice cream, as well as more of the people go for the swimming, either in the ponds or in the river or in the lakes. So obviously, since more of the people are in some water body, so the chances of the death would also be high. So here they are showing the concomitant variation, but neither sale is the cause of the death because of drowning. Neither death due to drowning is a causal factor for the sale. Right? So it provides only the necessary condition. The next one is the time sequence. Time sequence states that the causal variable should precede or occur simultaneously with the effect factor. Means the causal variable should not occur after the effect variable. Right? So it may be possible that something happens after the some other thing may happen. So why it is possible that there may be some random causes, or there may be some random matching, or there are something that is not at all related, but it is just a random fluctuation because of which we can observe any time sequence. So again, time sequence is a necessary condition, but not sufficient condition. Now we come to the next part, that is the absence of the extraneous variable. Means absence of all the external factors, external variables that may have the impact. So if there is no change in the extraneous factor, or there is no extraneous factor, there is no external factor. And if one variable changes, there is a simultaneous change in the other variable also, right? Then we can say with both the necessary and sufficient condition that they have the cause and effect relationship. So absence of extraneous factor constitute both necessary and sufficient condition for establishing causal factor, right? So whenever there is no extraneous factor and the explanatory variable changes, and there is a change in the explained variable or the dependent variable, then only we can say that they are connected with respect to cause and effect. So this is both necessary and sufficient condition. So this is the condition that we are going to discuss in detail. Now, how we can achieve control over extraneous variable, control over extraneous variables. One is the physical control, that we can physically control the change or the movement of the extraneous factor. So this physical control is possible only in some lab experiment, but it is not at all possible in some open environment or in some management related problems or a problem that have higher degree of connotation. Right? So this is possible only in the lab experiment, not otherwise. So physical control is not possible. The next one is the randomization, right? That we assign randomly, uh, means we assign random units to both the cause and effect factors, and try to control the extraneous variable. So randomization again in in uh, in oneself it is not possible to control or to make absent the extraneous factor just by the randomization. So this is not possible in the real life also, that only randomization can achieve absence of the extraneous factor. So now we come to the third part, that is the experimental design. So we will be discussing the experimental design, and definitely it achieves the control over all the extraneous factors. Right? So before going to the concept of experimental design, let us discuss some basic terms that we are going to use. So the first one is the experiment. So experiment may be defined as means of getting an answer to the question that experimenter has in mind. Means whether the tonic A is good or tonic B is good, whether advertisement will affect the sale or sales promotion will affect the sale, whether discount has some impact on the sale of the quantity or not, right? So this is a way to get an answer to the question that the experimenter has in mind. This is known as experiment. We are defining experiment in detail also. The next one is the treatment. Treatment is a different procedure objects under comparison in an experiment, right? So as we have taken the example, suppose we are giving tonic X, tonic Y, or tonic Z, and we have to find out whether a particular tonic has an impact or not. Right? So these are the different procedure or the objects under comparison. So they form the treatment. In the same way, we can have other thing also, right? That can constitute the treatment, like whether we go for advertisement or we go for the sales promotion in order to increase the sale for the kids, right? So they are termed as treatment. So here XYZ are the treatment, here advertisement and the sales promotion are the treatment, right? After that, we define experimental unit. So experimental unit is the material. It can be a non-living form, it can be in the living form also, to which is applied the treatment, on which treatment is being applied, and on which variables under study is being measured. Right. So suppose we are uh, we are considering uh, a person, whether the person or the customer would be affected uh, by advertisement or the person is got affected by sales promotion, right? So here the person is the experimental unit. Suppose we take unit as the shop, whether whether there is an impact on the sale of the shop through advertisement or there is an impact on the sale of the shop through sales promotion. So this is known as experimental unit, right? So any living or non-living person, non-living thing on which the treatment is applied and the variable under study is measured. That is known as experimental research. After that, we define the experimental error. So there is a variation in the measurement made on the different experimental unit, right? Even if they get the same result, right? So suppose we have two unit, unit number one, unit number two, right? Both are given the same treatment, TT, right? So there will be a variation in the results, variation in the method. Now, part of this variation is defined, systematic, or explained. And the other part is the random or unexplained. And this random part is known as experimental research. Right? So this is the unexplained part that we is constitute the experimental research. So what is the role of the experimental research? It provides the basis for the confidence to be placed in the inference that has been drawn from the sample to the population. Right. So lower the standard error, higher is the confidence. Higher the standard error, lower is the confidence. These are the some terms that we are going to use in future. Now, as we discussed, we are defining experiments in a broad manner, right? So, what do we mean by experiment? Let us take an example of agriculture example. Suppose we want to know whether seed quality has some impact on the yield or the output. So how that can be done? We consider some plots. These are the plots. where the seeds can be sown. Right now, here we are using a seed of low quality. This is low quality seed. This is the medium quality seed, and this is the high quality seed that is being used in this agriculture crop. But apart from the seed, every other thing, that is the soil quality, manures, irrigation amount, fertilizers, every other things remains the same, right? So this is known as experiment, right? So again, what do we mean by experiment? It is the manipulation or change of a variable or more than one variable. Here we are manipulating, we are changing the seed quality. So manipulation is being done here. And the control of other variables. Since the other variables like humidity, temperature, right, soil quality, irrigation amount, right, all other things are controlled, made constant. And after that, we examine the impact, whether there is an impact or not. Okay. So as per the discussion, the experiments has the three elements or the elements of the experimental design. One is the input. We have two type of variables. One is explanatory variable, which constitute variable under study. This is the explanatory variable, right? And we try to establish cause and effect relationship between the explanatory variable and the dependent variable, that is in the form of output. We have another set of the variable that I have already been mentioned, that is the extraneous variable, right? So these extraneous variables are the variables which are not present in the experiment. They are not present for study, means they are present or not used for the study. Better word is not used for the study. Means they may have impact, but we are not using, right? They are for the study, they are known as extraneous variable. Now, both explanatory variable as well as extraneous variable has an impact on the test unit. It can be in the form of some human, it can be in the form of some units or non-human. Okay. And here we get the dependent variable. So this is known as experiments, right? We are deliberately changing explanatory variable, like here, this is the explanatory variable, seed quality, and we are making other variables as constant, that is the extraneous variable. So we are controlling the effect of another variable and we examine the effect. Okay. So this is known as experimentation, right? Now, uh, as we have discussed about the research design, so here we are providing the necessary definition. So the principle of design, designing an experiment means deciding how the observation should be taken. So this observation provides the information should be taken. So answer a question is a in a valid, efficient, and economical manner, right? So again, it is related to designing. Designing means some type of blueprinting. Some type of blueprinting is being attempted. And why this is being attempted? So deciding how the observation should be taken to answer a question in a valid, efficient, and economical manner. So these are the characteristics. Now we have three basic principles of the experimental design as given by the Fisher. One is the replication that we will be discussed in detail. Other one is the randomization. And the third one is the local control. So these are the three basic principles used by experimental design as suggested by Fisher. Now, what is the role? Let us draw the Fisher's diagram. Here in the center, we have replication. Now, replication along with randomization They provide valid estimate of, so they provide valid estimate of the error or the extraneous term, right? They provide the valid estimate. Now replication in conjunction with local control, they provide the control of error or decrease of error. Okay, so replication along with randomization provides a valid estimate, and along with local control, it achieves control over extraneous factor. This is the Fisher's diagram. Okay. Now we are discussing these concepts in detail. Randomization. Randomization means choosing observation from the sample randomly and randomly assigning the treatment to the different doses. So it formed the basis for the valid estimate of the experimental error and to minimize the bias and to achieve independence of error. So the objective of using randomization is, the first one is the valid estimate for the experimental error. The next one is to minimize bias, right? So there won't be any bias there. The third one is to achieve independence of error, which is an assumption for all the models that we are going to use in this case. So it achieves independence of error. So this is randomization. Now, as we discussed earlier also, randomization along with replication provide the necessary condition for the validity of experiment. So this is the concept. Hopefully randomization is clear to all of you. Next one is the replication. Replication is actually repeat and repeat. Right? So a treatment is repeated a number of times to obtain a more reliable, right? As we go on repeating a treatment, we will be getting more reliable estimate that is not possible um, through a sample case or one observation case. So this is the general definition. Now, why replication is important? It provides an increase of the precision, right? So that everything would be balanced, right? So, so the precision uh, is improved as we use replication. Now, as we discussed earlier also, along with randomization, they provide estimate of the error. And along with the local control, they reduces the experimental error. So this is the part, this is the unit that is being used in both ways. The third one is the control of the error that is known as local control. It is when it is used when the error control is desirable. And how it is being done? Obviously, if we have to achieve something, we have to sacrifice something. So we um, restrict the randomization, right? So far, we are considering the full randomization. Now here, we restrict the randomization. Okay, so it gives us the local control. The confounding is also a method where we can confound more than one factors. So that can be a method to achieve the local control or the control of the error. Now we are going to study three research design. One is completely randomized design. The other one is, so one is completely randomized design. The other one is randomized block design. The third one is the Latin square design. So these are the three designs that we are going to study. So the first one is the completely randomized design. As the name suggests, that randomization is complete, is without any condition. So when it is being used to study the effect of different levels category of treatment of an explanatory variable on the dependent variable. Suppose we have a variable that is advertisement, right? And suppose A1 is the radio advertisement, A2 is the TV advertisement, A3 is the advertisement in the newspaper, and A4 is the advertisement in the social media. Okay, so um, they are the different category of the treatment. So study the effect of different levels of different category of the treatment on the of the explanatory variable. This is explanatory variable, that is advertisement, on the dependent variable, that is sale. Right. So for this purpose, we use the complete randomized design. Right. So as the name suggests, here treatments are assigned completely at random to the experimental unit. There is no bar, there is no control. The units are assigned completely at random to the experimental units. Now here, since we have full randomization, it does not have the third characteristics that is known as local control. So it uses only two principles of research design. One is the principle of replication. The other one is the principle of randomization. Okay, so it does not have local control. Now it does not have local control, so it has no control over error curve. Right? So, so how that is possible? Since it has no control on the error component, so we try to have every extraneous factor similar, right? Because if there is some variability in the extraneous factor, it will the results would be badly affected. So now, when in which situation it is possible that all the units should be exactly similar or the units should be homogeneous. So that's why this is the sentence that it is useful in the small preliminary experiment when experimental units are fully homogeneous. Means there is no um, there is there is no heterogeneity that may produce the extraneous effect. Right? So obviously this is a condition, so the its role or the application is much limited. Application is not much common, right? So means it is very restrictive application because it requires the experimental units to be homogeneous. Now, we are discussing the layout and the concept of the completely randomized design, that is the CRD. Suppose we have T treatment, like in that case, and IF treatment is replicated RI times. Means T1 treatment is repeated R1 time, T2 as R2 times. In the same way, TT is being repeated RT times, right? So we have T treatment and IA treatment is replicated RI times, right? So these are the replications. So total number of experimental units would be um, R1 plus R2 and so on. So that is the summation of I to T of RI. So these are the experimental units. If all the replications are same, means all the treatments are repeated equal number of times, means R1 equals to R2 equals to R. Okay, so it would be N is equal to T into R because every treatment is being repeated equal number of times. So this is N. Now in CRD, since the name is completely randomized and this is full freedom, so three treatments are completely applied at random to the N unit. So T treatments are applied completely randomly, right, to the N unit, such that IA treatment appears RI time. So there is full freedom, right? Like the first treatment is being replicated on 5 units, the second may be replicated on the 6 unit, the third one is replicated on the 7, fourth one is replicated on the 5, and so on. Okay, so they are completely at random to the N units. Now, for the layout, that will be starting with the analysis. Observations from, right, suppose we define Yij. Yij is the observation of the jth replicate. This is the repeated of the ith treatment. So it is equals to the general effect, that is mu, plus effect due to ith treatment, that is tau, plus random error component, that is EIJ. So this is the model that we use. Now here, mu and Ti are constant. Okay, they are the constant, and sigma of Ri tau I would be 0, and all the error terms are identically independently distributed normal variance. Okay, so this is the condition for the error term. Right? So this is the Ij is equal to mu I plus Ti plus Eij with this condition. And for the analysis, we require one-way ANOVA. So here I am explaining a bit of one-way ANOVA. Just a moment. Though we have covered one-way ANOVA earlier also, but here we will be discussing. So here we will be examining H naught as tau 1 equals to tau 2. These are the different treatments. Is equal to tau 3 is equal to so on. And H1 is at least one Ti is different from others. Okay. So for that, we construct the ANOVA table. So to run the one-way analysis. The first one is the source of variation. The next one is the degrees of freedom. Next column is sum of square. And then we have mean sum of square. And in the end, we have the variance ratio. Just a moment. We have F ratio or the variance ratio. Sources of variation. The first one is the treatment. Since this is one way only, this is one way. The other one is the error. Just a moment. The next one is the error or the residual. And the last one is the total. We have n observation, that is summation of, as we have mentioned, summation of Ri's. I varies from 1 to t. So n is the number of observations, so the corresponding degrees of freedom would be n minus 1. T are the number of treatment, so that is t minus 1. For error, we have n minus 1 minus t minus 1, so it would be n minus t. The first one is sum of square due to treatment. The next one is sum of square due to error that we have discussed in regression in quite detail, and this is TSS. So SE, sum of square due to error or residual, is the subtraction of SSTR from TSS. And for mean sum of square, which is simply the sum of square divided by degrees of freedom. So the first one is MSTR. This is SSTR divided by degrees of freedom, that is T minus 1. The next one is MSE, which is SSE divided by n minus t. And okay, and the variance ratio is MSTR upon MSC. Right? Now this F follows F statistic F statistic with degrees of freedom t minus 1 and n minus t. This is n minus t. Okay, right? It follows, right? And accordingly, we decide whether to reject the hypothesis or not to reject the hypothesis. Right? The second one, the second research design is the randomized block design. Right? So as we discuss the main drawback, those CRD is very simple to apply, right? And that was a starting research design. But CRD will seldom be used if the experimental units are not homogeneous, because CRD has no local control. So CRD cannot be used if our experimental units are showing the heterogeneity or the variability. So for that, we introduce randomized block design. As you read this, this is randomized block, not complete random. It is a randomized block design. So so the RBT takes care of variability among units. So it is possible to separate out the effect of one extraneous factor. It goes with one extraneous factor. And it is very popular because it uses all three principles of experimental research as propounded by R.A. Fisher. One is the randomization, another one is the replication, and the third one are the local control. Okay, so it uses all three experiments, or all three principles. I will be explaining how the local control would be used. So suppose there are three treatments and each treatment is being replicated R time, means each treatment is repeated equal number of times. Right? So there will be n is equal to RT experimental units, and these units are not homogeneous. So this is the field that we are getting. Now, actually RBD consists of two steps. First, we have to create the blocks which should be homogeneous, and after that, in the each block, we will be assigning the treatment. So what is the first step? The experimental units are allocated to R homogeneous blocks, right? So the number of blocks should be equal to the number of replication, that is R. So the experimental units are allocated to R homogeneous blocks, and these blocks have much, um, much homogeneity, right? R homogeneous. And the second thing is number of units in a block is equal to number of treatments, right? Suppose number of treatments are 4 and the number of and and the number of blocks are 5. So we require 20 experimental units. And in the first block, there will be 5 such blocks because number of blocks is equal to um, is equal to the number of blocks is equal to common replication number. So we have 5 blocks. These are the 5 blocks, and each 5 blocks we have 4 units. 1 2 3 4. 1 2 3 4. 1 2 3 4. 1 2 3 4. 1 2 3 4. Okay, right? So experimental units are allocated to R homogeneous blocks, and number of units in a block is equal to number of treatment. Right? So as we have discussed here also, number of blocks is equal to number of common replication because each treatment is being replicated equal number of times. Okay. Now here each block is internally homogeneous, maybe externally heterogeneous. And the condition of the complete randomization is related to the unit should be homogeneous in nature. Now, since the units inside the block are homogeneous, so we assign treatment at random to the unit of the block. And remember, we have taken number of experimental units in a block is equal to number of treatments. So all the treatments may be applied inside the block, inside a block. right? So here we assign treatment at random to the units of a block. They are assigned. Now, in the initial completely randomized design, there is no restriction on the randomization. Randomization is done on the whole sample. But here we are restricting the randomization. Why or how? We are we perform randomization is to be done or is to be performed afresh for each block, right? So the randomization is being limited to a block only, right? So that's why it is a condition that randomization is to be done afresh for each block. So thereby we are restricting the randomization. So by restricting the randomization to a block, not allowing them to a field, we achieve control over extraneous factor or the is error is being controlled. Okay. So here we are restricting the randomization, and in this way we are having an impact on the extraneous factor, right? Which is not possible in the completely randomized design. Now, as we have observed also that each treatment would have same number of replication. So like in that example, each treatment, whether this is T1, this is T2, right, or T4, each would be repeated 5 times. Right? So each treatment has number of replication. This is the most popular research design, but the block size, we take block size as the size of the number of size equals to the number of treatment. It should be small, right? Because there is a condition that blocks should be homogeneous. But if we have bigger blocks, then blocks may not be internally homogeneous. So this is the condition. It has simplicity, flexibility, and validity also. Right? So this is a randomized block design. Now here we are discussing the analysis or the layout that is related to randomized block design. So here Yij is the observation of the ith treatment for the jth block. Here value of I is equal to 1, 2, 2 T and J is equal to 1, 2, 2 R. Number of treatments are T and number of the blocks are R. So this is the observation of the ith treatment for the jth block. This is equals to the general effect, which is a constant, and effect due to IS treatment, effect due to the jth block, that is Bj, plus the random error component, that is Eij. Here, summation of tau I equals to 0. Summation of Bj is also 0. And this Eij follows or is identically independently distributed normal variance with zero variance, with zero mean and the common variance, right? So this is the layout that we use. Now, for this analysis, we use the two-way ANOVA that we have studied earlier also. Now we will, just to have an idea, we will be discussing the basic concept of two-way ANOVA again. So I am having one more. So now we are discussing the analysis for RBD. Is two-way ANOVA. Is there are two causes for the variation. Two-way analysis of variation. So as we discussed earlier also, here, just a moment, we have hypothesis. One is H0T, that is for the treatment. It means T1 equals to T2 equals to T3 and so on. All the treatments are same or all the tau i's are 0. This is for R. And the other one is H2B, means all the blocks values are same. B1 equals to B2 equals to B3 and so on. Means all the bj's are 0 for all j. So these are the two hypotheses that we use. Now we will be constructing the two-way ANOVA table. The first one is sources of variation. The next one is the degrees of freedom. Next one is the sum of square. The last one is the variance ratio. The first is the blocks. The next one is the treatment. Next we have extraneous or the error, and that is the total. As we have discussed, the number of observation here would be RT, right? So number of observations would be N equals to RT. Total number of observation would be RT minus 1. Now the blocks degrees of freedom would be R minus 1. For the treatment, we have T minus 1. And for the error, we have RT minus 1 minus R minus 1 minus T minus 1. Upon solving, you will be getting R minus 1 into T minus 1. So these are the degrees of freedom for the error. We have sum of square due to blocks, SSP. We have SSTR. We have SSE. Right? And here we can have MSB, that is the SSB divided by degrees of freedom 1, R minus 1. We have MSTR, that is SSTR divided by T minus 1. Next, last one is MSC. This is SSE divided by the corresponding degrees of freedom R minus 1 into T minus 1. And for the variance ratio, we have F0T, that is MSTR divided by MSE. Right? Though the another one is not required, but even if we are going with that, F0B is equals to MSB divided by MSE. Now F0T follows F distribution with, in the numerator we have MSTR with degrees of freedom T minus 1, and the error is R minus 1 into T minus 1. And accordingly, we decide whether to accept the hypothesis or to reject the hypothesis. Okay, so this is the analysis that we discussed related to RBD. Now, RBD is the most popular design, most useful design, because number one, it achieves local control by creating the blocks, and um, it is otherwise also it is free, so we can have any numbers of replication. So that's why that is the most popular design. Now we are going to cover the third research design, that is the Latin square research design. Now, as we discussed in the RBD, is the first research design that uses control of error or have local control. So in that case, local control is being achieved one way by the blocking. Okay. Now we are going to cover the next research design, that is the Latin square research design. Here the principle of local control is being used two way by grouping the units in two way, one as per the row and as per the column. Right. So here local control is being implemented or is being used row wise as well as column wise. Right? So in that way, this as far as local control is concerned, it is supposed to be better than the other research design. But there are certain issues that we are going to discuss. So each way corresponding to source of variation among the units. Row wise, suppose there is a source of variation that is A, and the column wise, suppose there is a source of variation that is B. So here we try to achieve control both ways. So it allows, since there are um, two ways. So it allows the control and measurement of effect of two extraneous variables, one on the row side that is A and one on the column side that is B. So it allows the control and measurement of the effect of two extraneous variables on the uh, dependent variable. But the only condition is that two extraneous variable have same number of categories, right? Means if the A has M category, that is I varies from 1 to M, then B must have M categories only. That is J from 1 to M. Okay. So two extraneous variable has same number of category and they are equals to the number of treatments. The number of treatment would also be M. Right? So number of treatment equals to number of replication equals to M. Everything is there. Now, for that analysis, we require M rows, M columns, or an M treatment. So M cube observation, M to the power 3 observation, right? But here, that is uh, uh, that is the complete concept. But here we use incomplete three-way layout. So here we consider under the condition that total number of experimental units should be m square. Remember, not m3. And that is why this is known as incomplete. So the total number of experimental units should be m square only. And they will be arranged in the form of m rows and m columns. I will be showing you according to two sources of variations. Right? So this is. So one source of variation is this way, row wise, and they have five category, that is 1, 1, 2, 3, 4, 5. Here another source of variation, suppose this is A, this is B, that is the column size type, and here also the number of replication should be exactly 5 only, because this is a condition that number of categories in the row and number of categories in the column must be same. So it has the same 5. Right? Now, these are the treatments. Treatments are A, B, C, D, and E. There are 5 treatments. So, number of rows equals to number of columns is equal to number of treatment that is being applied. Now, they are being applied here. So, once they are applied, you can check that in a row or in a column, a particular treatment would be repeated once only, like A here. A is being repeated once only in this row and in this column, right? Suppose if we take another one, that is B. So B is repeated only once, right? As you see, D, A, E, C. So B is repeated only once in its row as well as in its column. So we have E, B, A, D, C. It is not being repeated. Like here, let us consider the D, right? So here D is being assigned once in a row that is a single D, and once in a column, right? So this is the condition that we impose. So the M treatments are allocated to these M square units at random such that each treatment occurs, right, once and only once in each row and each column that I was explaining just before. So that's why this is known as incomplete three-way layout. So instead of M cube observation, we use M square observation along with the condition that number of treatments equals to number of rows is equal to number of column, and each treatment would be repeated once and only once in each row and each column. And here the allocation is orthogonal in nature. So this is the Latin square research design. Now here the layout that we use is YIJK, where I varies from 1 to A, that denotes the factor A level, right? That is the ith row, where value of I would be 1, M. And in the other one is the J. J is also taking M values. So B is at the J level, another source of variation that is B, that is at the J level, that is the jth row. And here the values of J also lies from 1 to M. And the third one is K, that is the treatment. So number of treatment would also be equals to M. So C is at the kth level, that is the kth treatment. So this is the Yijk. Now here, mu is the general effect. This is the effect due to ith row, effect due to jth column, and effect due to treatment. And this is the error or the random component part. Now here, mu, alpha I, beta j, tau k, all are constant. Right? So condition is sigma of alpha I over I would be 0. Sigma of bj would be 0. And sigma of tau k over k would also be 0, right? So this is the condition, right? And and since this is an incomplete layout, so here the triplet ijk takes only m square values instead of possible m3 cube values, right? So that's why this is known as incomplete three-way layout. Right? Now I am taking one more slide. So to explain the ANOVA table for this case also. So now we are discussing ANOVA is an incomplete three-way layout for Latin square design. Okay? And we take the hypothesis as H01, that is all alphas are same, H02, all betas are same, and H03, all tau ones and H1 is at least 2 are different. So here we are attempting the ANOVA table. The first one is sources of variation. The next one is the degrees of freedom. Next one is sum of square. The last one is the variance ratio or the F ratio. Just a moment. This is for the first source of variation, that is rho or A. This is for the second. This is for the treatment. Next is the error. And the last one is the total. So the first one is due to A, that is the rows. Since they are m, so m minus 1. Total number of observations would be m square. So degrees of freedom would be m square minus 1. This is the total. The next one is due to B. It is due to columns. Here also we will be having m minus 1. The third one is due to C or due to treatment. Also m minus 1. And the next one is the error component. The error would be m minus 1, means subtracting and the sum of m minus 1 plus m minus 1 plus m minus 1 from m square minus 1, we will be getting m minus 1 into m minus 2. This is SSA, this is SSB, this is SSC or SSTR, this is SSE, and the sum is TSS. And mean sum of square is always sum of square divided by corresponding degrees of freedom. So this is MSA, that is SSA divided by M minus 1. The next one is MSB, that is SSB divided by M minus 1. Then we have MSTR or MSC, that is SSTR upon M minus 1. The last one is error, that is MSC, that is SSE upon M minus 1 into M minus 2. Now, if we are interested only in the treatment part, so that is MSTR divided by MSE. Now, this FTR follows F distribution with, in the numerator, we have MSTR. So, degrees of freedom would be M minus 1 with M minus 1, and error degrees of freedom are M minus 1 into M minus 2 degrees of freedom. So they follow the F M minus 1, comma, M minus 1 into M minus 2. Okay. So accordingly, we decide whether to accept the hypothesis or to reject the hypothesis. So this is a broad description of the ANOVA, of the uh, three experimental research design that are used to achieve the cause and effect relationship as per the controlling of extraneous variable. In the first one, we don't have that much control, means local control is not being used, but the local control is being used in RBD as well as LST, right? And we have already covered the ANOVA part. So from there, you can uh, go through that notes. So that would be helpful, right? So this is about today. So hopefully these concepts are clear to you. And if you face any problem, you can always discuss these things. So this is for today. And I will be sharing these slides with you. Okay. Thank you.